Okay, let's get started. I have to admit it was nice seeing everyone on Thursday instead of just half the class, actual faces. It's not that scary that people see you. I mean, after all, when you can go in person, right? You walk in the class and we get to see you. Before we get started, as you all probably know, registration for graduate students starts this week for spring semester. Couple reminders. If you're an international student on an F1 visa, you have to be enrolled in at least one course in the program that's listed on your I-20. And in particular, our web and mobile certificate program is not on your I-20. So you have to take a regular CS course to maintain your visa status. Now, for some of you, if you're an international student, next semester, you may only need to take one class to graduate, which means unless you want to pay a lot more money, you basically are stuck taking only a CS course, right? Because the web and multiple courses will not count as that one, and you need a class on the regular CS side. Clear? And for international students, I had a few questions today, and apparently a number of students had questions yesterday in class with Dr. Wang. Typically, a lot of Indian students want to go home over the Christmas break and then come back. And they're asking about will there be any problems getting back into the country if they don't have a face-to-face course they're taking. And basically, the only answer we have is, that's completely that's completely a visa issue, which San Diego State has no control over. And particularly this year, things have changed quite a bit, and graduate advisors only get our advice from International Student Center. And typically, I have to ask them a very direct question to get a response, because they're very cautious about giving answers out like that. And so from the department's viewpoint, we don't know if you'll have trouble getting back. In theory, you shouldn't, because you have a valid I-20. But still, when we talk to them about incoming graduate students and starting in the spring, they told those students, well, when you go for the interview, tell them, you will be taking a course that has hybrid face-to-face content. And they said that should be enough, but they also told us we should make sure the students basically print out their schedules so they can point to the class that has face-to-face. So that's all I know about that issue. Any questions? There are a bunch of blank stares, like. Okay, let's get started then. And we will go through standard process. Keep on thinking that perhaps I should share my screen before I start the class. But it always seems to me that it's nice to see the instructor. Not that I consider myself a beauty, but you know, in this time when we're spend all this our life inside our bedrooms and living rooms, certainly nice to have see a face a little bit before we become a little dot on the screen. Okay. Well, at this point, you've seen enough patterns, you know the basic structure. And so we're going to look at a few patterns. The first one, the composite pattern. Oh, darn. There's quite a delay this time. Let me see if I can figure out why we got that delay. And we'll see what happens. So motivating example, when we build a GUI, right, we have, you know, buttons and dials and sliders, you know, and text areas, etc. We also have, you know, what Java calls panes, so we can group things together and move the pane around. So we have windows and widget containers, and then widgets. And then the problem becomes, how do we deal with the fact that when we build our GUI and want to interact with the components, we have two different types of things, you know, widgets and widget containers. Now, I did realize today that I need to come up with a new example to motivate this, because a lot of the modern GUIs are hiding this problem. So in Android and iOS, the old way is you had a GUI builder, and so you could drop in a pane or a container and you wouldn't notice this problem. And the new ways that they do it even hide it more. Thought of that too late. So one way is, well, when I build my GUI, I have a list of buttons, a list of menus, a list of text areas, containers. And then the problem is when we need to update things, we then have to have a bunch of separate for loops for each of the list to tell things that update themselves. And this is not going to, this is sort of unpleasant, right? To have this big case statement of all the different types of things we might have in a window. Particularly if we create new types of widgets or new types of containers, we then have to create more lists. Clear enough what the issue is? Everyone's got the election results on a screen. They're watching, like, don't worry, it's too early. watch for that. So one way is, well, we can create a parent class or an abstract class for the widgets, right? And separate widget containers. And then we're down to 2 lists, right? One for widgets and one for containers, which is clearly an improvement. And this leads us to the direction of the composite pattern, where what we do is we create an abstract class or interface, which for the pattern they call a component. And one of the subclasses is a container, right? And the intent is, right, to compose these things in tree structure and treat individual objects and composites uniformly. So the goal is the clients don't have to know which one's a button and which one's a window, which one's a widget container, right? Because we can now have a list of components, and some of those components may be a button or a menu, and some will be widget containers. However, there is a slight conflict built into this pattern, and that is we want to be able to treat object and compositions uniformly. It's the same thing, but composites have operations that individual objects do not, right? If having a container, that usually means I can add things and delete things from that container, and we don't add things and delete things from a button, right? So individual objects, we don't have this add and remove operation, whereas the composites we do. So how do we treat them uniformly? So we'll see several ways of doing that. So the composite pattern, usually the abstract class implements as much default behavior as possible. Then all the subclasses override methods they need to. And basically the container needs to override them all, because usually what it's going to do is it's going to take that method and broadcast it to all the things inside of it. Right, so the widget container, right, is going to then, pass on whatever method happened to all the things it's holding. So the question is, where do you want to implement the container operations, the add, delete methods, etc. So one answer is put them in the parent class. And that means all classes can be treated alike. Can anyone see a problem with that?
Well, what happens when you try to use the widget container operation on something that isn't a container?
Right. So one thing you do is just have that be a null operation, right? The problem with doing that is if you're trying to, say, add a widget to a button, that's that probably means that your logic is incorrect. And if that operation is null operation, then you're not going to realize that there's something wrong with your logic until later, right? So that's the problem, right? So yeah, decline those only in the widget container is safer because you're not going to be able to add something to a button. Um, but now if you actually want to add things at runtime to a container, we either need a separate list of containers anyway, or we need to type check to see what type it is. Now, this does happen in Java Swing and Java AWT. But what happens there is typically you create the GUI interface at one time, and then you don't mess with it, right? You're not adding, not deleting things. And so typically you don't have to worry about adding a component at runtime. You typically will hide it so it's not there and then display it when you want to see it. So in that context, this issue doesn't come up because the main use case is you don't, when you set up the GUI interface, you construct the tree, and then you don't go and call widget container operations yourselves on the containers. So the text talks about a number of issues. One is, do you want to allow parent pointers in this tree? And do we want to then have the parent pointer be a type component, even though we know it has to be a container, right? Other problems are, can we lift everything from the widget container up to the component by having a list of operations or list of components? Same problem with having operations. How do we deal with ordering of children? How do you delete things? And so this is, the intent. So this is when we want to combine parts and groups together, and we want to ignore the differences. And the question is, what circumstances do we want to do that? And one example is the interpreter pattern. So let's take a look at the interpreter pattern. And the goal here is, of course, if you've got a language like Java, we're not going to use an interpreter, we're going to use a compiler, right? But there are lots of times when we are dealing with a small little language and we don't want to build a compiler. Pretty much anytime you read a file that has any structure in it, you're basically running a little interpreter to parse that file. And actually, it's too bad that we don't offer a compiler course. Because whenever I talk about compilers or interpreters, you know, main reaction is sort of blank stares, like, well, when would we ever want to do that? And after you take a compiler course and spend all that time thinking about parsing and compiling and generating code, what happens is you start to see that same issue occurring in multiple places we wouldn't normally see it. This normally happens to me when I learn a new idea. It's like, oh, I never thought of that before. And then once I understand the idea, I start seeing applications where I wouldn't normally. So if you're ever going to take a compiler course, you'd probably see far more places where parsing and interpretation of a language occurs. Has anyone taken a compiler class? Just one person.
Yeah, I have.
And so did you notice after you took the course that you saw places that you normally wouldn't think of as?
Not to the same extent, I don't think, as
Okay.
you're describing.
Every time I want to read a file, I just like, okay, how do I do this? What's the structure? How do I do that? Particularly if it's some dependencies in there. So the goal here is you have a language, usually a small language, usually a grammar. You want to build a system to represent a program in that language and then evaluate that program, right? So, you know, if we have a language defined by a grammar, you know, here we've got a rule and it's followed by three, it's generated by three other rules. Each one of those rules will have, you know, statements that they compose with, right? And so for each item in a grammar, we're going to create a little tree structure like this. Currently, there's a 3-second delay in my drawing, right? So a very simple example, you know, Boolean expressions. So we can define what a Boolean expression is. So here's, you know, a small grammar. You know, a Boolean expression is a variable, a constant, ors, ands, and not, or another Boolean expression. An and is, in this case, you know, two parentheses, two Boolean expressions, and an and in between, the or, the not, right? And a constant is either true or false. And a variable, we'll say it's some sort of string, and we won't go into what a string is. So here's our grammar, right? Which means now using an interpreter pattern, what we're going to do is we're going to turn each one of these rules, right, into basically a little tree. All right, so we can look at this expression, right? And that becomes, we can translate that into a tree structure, um, as shown here. And once we have this, we want to evaluate it, right? Since only one person seems to have taken a compiler course, only one person probably recognizes it as basically a parse tree, right? So basically, we take an expression and create this parse tree. Now we want to evaluate it. So how can we do this? Well, we can create an interface for Boolean expressions, and we'll give it two operations, evaluate, and a toString, just so we can see what's going on. Here is my AND class. It needs my two operands, left and right. And then my evaluate function, right, is just, well, first evaluate left, and then evaluate right, and then AND them together. And actually, if ands are in this language are short-circuited, we may not evaluate the right one. And once you see the AND class, right, the OR class becomes obvious. Constant class, a constant class is either true or false, right? And so the evaluate function there is just return whatever its value is. If you've got a variable, then what we're going to do is we're going to pass in a context which contains all the names of variables and the current values. And to evaluate that, then you just go into that context and get the value of a particular name and return it. In this case, my context is going to be hash table. So here is some code to create the parse tree for this expression, right? The left-hand side has an OR, and it has a constant true, and it has a variable called x. The right one has a variable w and variable x again, and and then I'm going to OR them together. And then to evaluate the expression, I'm going to call evaluate on all and pass in the context so we get the value of the variables. And it's going to return the result. I think Kong will agree that this is simpler than building a compiler? And now if we want to evaluate the same expression with different values for x and w, we can just deal with the context and then evaluate again. So far, so good. So consequences, it's easy to change, extend the grammar. To extend the grammar, we just add more rules. That means we just add more classes, right? You know, once we know what the grammar is, it's pretty straightforward to implement all those classes. You don't want to be, if the grammar is very complex, you don't want to use this pattern to interpret Java, right? Java is a fairly complicated language, and when you look up the grammar, it goes on for pages and pages and pages. It's just not going to work. We get to talk about another pattern we looked at. If you want different ways to interpret expressions, we can use a visitor pattern, right? Why? Because we're going to have this parsed tree that contains different types of nodes. And then the visitor, right, can be used to go to each node one at a time. And we can then build different visitors to do different things for each node. However, if the language is simple enough, it may be just easier to deal with it directly. You know, Boolean expression, you might be able to just, in Java, it'd be hard to deal with, but in language like Python and some other dynamic languages, you can probably just take that string and evaluate it directly in the language with eval. So now, how is this an example of the first pattern? What was the first pattern?
Well, we're kind of, we have like the constant and the actual like a list of expressions in the same, being used in the same manner.
Yeah, so we have, in this case, you know, the leaf items are going to be individual things, right? And then the internal nodes are actually composite things, right? Because an OR contains two regular elements. And so this expression tree or parse tree is a composite tree. So we basically have two patterns that use the composite pattern. One is one is interpreter pattern and the other one's a visitor pattern. Okay, now one important thing, the pattern does not talk about how to parse the expression to build a tree. And well, we've got one student who can testify that parsing can be tricky, right?
For sure.
Particularly if it's the language is context sensitive, right? And it's like you have to know which context you're in to know which rules to apply. And so a lot of the compiler course talks about how to parse the language. And that's one reason why most computer science departments, have these theory courses on languages and other patterns that come into play. The terminals, if they're repeated many times, then we can use a flyweight pattern to reduce space. We haven't talked about that yet. The composite we talked about. And then iterator pattern can be used to diversity if we need to, and the visitor can be used to create different types, ways of evaluating the expression. Let's see, one. So one place I know where this is used is in these systems that want to help students learn how to program. And they do it graphically. And so what they'll do is they'll give you, the students, a list of different operations they can perform on the side. And they drag those things around and connect them together. Right? And so you have a loop here, a for statement. They'll connect it to some object so they can move the object around. And so what they've done is they've created a little language that will, say move this thing around, and for each rule they've implemented a visual component, and then they allow the student to grab these components and combine them together to create a program, which is represented by a abstract syntax tree in the background. And then when the kid presses go, right, you basically then just interpret that system, right? Yeah, and so Alonso was saying they did something like this. Yeah, they did something like this with business logic. Yeah, and it's a common.
My implementation was really bad. It had a lot of for loops in Python.
Yeah, and it's similar context is probably some of what you had to do is, what do you do if you have a manager who wants to make queries to an SQL database, but they don't know SQL, and they right? They don't want to learn, right? And so what you do is you figure out, sort of a subset of queries you want them to be able to make, and then you break it down into little pieces, right? So you're creating a little language which you're then going to interpret into SQL, right? And so we can then, right, build classes to do that. And then if you need a GUI, you can attach the GUI allow the manager to put together this query. And again, it's, since, students haven't taken the compiler course, you probably don't think this way, but, another example of creating a language is, most of them are dealt with when it comes to querying a database SQL, they provide some non-SQL-like way of doing that, right? But what they're doing is they're creating a little language that they can say, here's the rules, and you build a construct in that language, and they're just interpreting that language into SQL and then sending SQL to, right, database engine. Any questions? My goal is to make this part of your next assignment. I'm trying to find a new little language to use. We'll see. Third pattern, the prototype. This pattern is one in which it's easy to understand what the pattern is. The issue more is when does it make sense to use this pattern? And the prototype is a creational pattern. And typically when we need a new object in a language like Java, we say new class name, right? And put in arguments. What the prototype does is, no, we're going to create what they call a prototypical object. And then we want another one, we're going to make a copy of that object, right? And so we create new objects by copying existing ones, right? So we start off with a set of prototypes, and then we copy them, right? And they give these fancy examples. Easiest one to explain is the bottom one. You have a class. It can only contain a few different states, so those states may be complicated, may only be a few valid states. So we could create one or several, all those states, and when we know one, we just copy that existing one. The second one, in a language like Java, we can't specify a class at runtime, right? We do a compile time. When we say new class or new foo, that's a compile time construct. And if you want the flexibility of at runtime deciding, oh, the user inputted this, so I want to build that, create that class, without building, complicated case statement. What we can do here is we can create a bunch of prototypes, give them labels, right? And then basically hash into that table to get the object we want and then copy it. The third one, well, we looked at the abstract factory pattern, right? Where you have a factory and you have multiple methods returning different things. And the example is, oh, we're going to create a factory for Windows and a factory for Mac and a factory for Linux. And the factory is going to return, menus and buttons and dials and all the various things. Well, one way to implement that is just to instantiate a bunch of objects for Windows, if it's Windows, and then when a new one, we just make a copy, right? So one example I've come across that's used in the industry, at least it was a number of years ago, typically when you go buy insurance, there's various standard policies, right? Buy a car policy, well, look, in California, the state requires certain minimums, right? So there's basically different categories. Here's the minimums you have to have. And so, typically an agent will say, here's, we'll start here, and then do you want more or less, right? Here's the average, here's a minimum. Oh, you have a high paying salary and you've got $1 million of stock options, right? And you drive a Tesla, maybe you'll want to start here because you don't want someone suing you and taking away your stock options. And so they customize it. And so there's some insurance companies would, what the program to do is you create a prototype object for that particular policy. And then you make a copy, and when the insurance agent was giving you various options, you would either modify that prototype copy they just made, or you basically store the delta between the actual prototype object and what the customer actually wanted. And of course, one way to do that is to use a decorator, right? So you have a copy of that standard policy, then a bunch of decorators modifying different parts of the policy. That sort of makes sense. Of course, the one issue is when you copy something, how do you copy it, right? So what happens when you have an object here, a door, and the door has references to other objects? So, a room, several rooms, and each room has a reference to other objects. So when I copy the door, we have to be careful because sometimes when you copy, you only copy the top level object. And then as shallow copy example shows here, then we have two door objects pointing to the same room objects. which means now if one of the use one of the doors to modify the room object, our copy has it too, to change. Right, and so we can start worrying about how deep you copy it. Now, I once had a student who said, yeah, in our company, there's like N different ways of copying objects, shallow and deeper and really deep and not so deep. And it got to the point where what was happening is people weren't quite sure which one to use. And so to be safe, they created another way of copying for their particular case, which just made the situation worse, right? Next person comes along, now there's N+1 ways of copying, like which one do I use? I know, I'll create another new one just so I don't have to figure it out, right? So this is one of the issues you have to worry about in prototype. How deep do you copy? And if you're going to be making changes, you probably want to copy all the way down. And then, of course, there's a famous problem, which I have given students before to solve, is what happens if you have a circular reference, right? A simple reference would be if the room actually had a reference to the doors in it. And so now I got a circular reference, and how do you copy that? This one is fairly easy to solve. It gets more complicated. If for some reason a table had reference to the door, it's going to be harder to, it becomes a bit more of a challenge to figure out that you've come back to where you've been. And when you copy this, you don't want to have going into the copying over and over again, because everyone see the difficulty if you have a circular reference? How long do you think it would take you to figure out how to do it? No one wants to comment.
When you're copying, you would have to keep some kind of context, or I'm not entirely sure.
Well, there's two ways of doing it. One is if you can mark each object as you reach it and copy it. So when you come back to it, you see it's marked. But that requires you to have space to mark it, right? The other one is you just keep a list of all the things you've seen before. And every time you go to a new one, you then check to see if it's in that list. All right. It's the same problem you have when you're doing garbage collection and you do a sweep of memory. You have the same problem as when objects point to other objects and point back again. When you're sweeping, you start with a known object and you start tracing all links down to mark all those objects as being safe. You you don't want to get in a circular reference and keep on going over and over again. So you have the same problem, right? You go, and you come back and say, okay, I've already been here, so I don't need to follow this link anymore. But in that context, usually you have control and you have a space to mark it as being seen before. But it's the same problem. So the sites, piece of information. There are languages which are prototype based. The most well-known is JavaScript. But you should know about the language Self. Self was developed about the same time as Java, so in the mid-1990s, a little earlier. And it was, unfortunately, it was developed at Sun Microsystems, where Java was developed. It was, one of its design goals was to see if we could make a dynamic language as fast as C or Fortran, right? So think of Python being as fast as C. Wouldn't that be nice? And of course, they have to remind you that a lot of the numeric packages in Python are actually Python wrappers around C code. So if you think those things are fast because Python's fast, you're wrong. They're fast because Python is running C code. So Self was very close to the performance of C and Fortran, and it was an object-oriented language, but it did not have classes. It had prototypes. You built a prototype object, and then you would copy it. Like I said, unfortunately, since it was developed at Sun at the same time Java was, Sun was not going to promote in a big way two languages. So Java won, and Self never made it past the experiments phase. You can still get it and run it on Macs, but now JavaScript is a prototype-based language. You can do a lot of copying in JavaScript. So here is one example. This is what JavaScript calls an object, which is basically a hash table with a key and a value. And so object create function will make a copy or from a prototype object. And we can, change a prototype. There's also I believe they call it a spread operator, which allows us to make a copy. Less syntax. Unfortunately, that copying, like the clone in Java does a shallow copy, doesn't do a deep copy. But that's not why JavaScript is called a prototype language. The reason it's called a prototype language is each object has a prototype attached to it. And when you're looking for a property, that's what they call fields, or a method in an object, it looks in the object. If it's not there, it looks in the prototype of that object. If it's not there, it's going to look at the prototype of the prototype, and it keeps on going down that chain until it runs out in the prototype chain. Yeah, well, you don't worry about that. Here's an example, creating a JavaScript class called rectangle. And I can now, when I create a rectangle object, there's two different ways I can access the properties, either with the dot notation or with the standard array notation. Now for the prototype example, here I create two classes, the cat and the dog. And then I can instantiate, a dog object and a cat object. And I'm asking the cat object, give me food. And the result is undefined, which is JavaScript's way of saying it doesn't exist. And now I give object a color. I give object prototype if a value called food, and I also specify cat's prototype of size. And now when I ask Fluffy for value of food, I get back a mouse. Why? Because it's based on a prototype, and that prototype has changed. Right? I can ask the size, and I get back a value because we changed the prototype of cat, right? And so Fluffy immediately inherits that value. Color is not defined because the prototype chain for the cat object contains the prototype for cat class and the prototype for object, but not object itself. Are there any JavaScript programmers in the class? Just one, two. Yes. What can I say? There's an organization that does a survey of programmers worldwide. It's not a scientific survey because people volunteer, but they get like 10,000, 20,000 programmers worldwide to fill out the survey. And the number one language used by these programs worldwide was, by a large margin, JavaScript. Why? Well, because if you want to build a web application, the standard is to use JavaScript. All right, so this is but this prototype issue in JavaScript allows you to do some things that can't be done in language like Java. Nature language changes because of it. All right, and we get, when we change a prototype of object, that change reflected in all the objects in the system. So it's not something you want to do in JavaScript, and that's why spot return mouse, but we can change that, override it by changing prototype for dog. And just to make sure that you realize JavaScript is not like Java. Basically, JavaScript classes are just syntactic sugar for functions. So here I'm declaring a class of type rectangle, and when I ask for its type, it's a function, right? So when you create a class in Java, it really is creating a function behind the scenes, and it has, when you ask, what properties it has a prototype, has a length, which is a number of properties, and it has a name. And basically almost everything in JavaScript is an object, which is just basically a hash table. All right, so when I create this function, it's a hash table, contains a length, the name, the arguments, the prototype, and caller, which means another weird thing in JavaScript. When a function is called, you can find out inside the function who called it and do different things based upon that. Here's a slight detour into JavaScript. Questions, issues? Now, there's only 5 minutes left. I don't think we want to get in the middle of the builder pattern and then resume next time. So we'll stop here and then look at the builder pattern on Thursday. Any last minute issues, questions? No, there's a bunch of blank stares. Oh, yes.
Have a good night.
Hmm?